Okay, Unit 3, Energetics and Kinetics, IB Topics 5 and 6. Now, in fact, it's almost entirely energetics. The kinetics portion is very short, so really it's a unit on energetics. It's a little energy diagram. You'll understand this at the end of the unit. 5.1, Measuring Energy Changes. This is called a calorimeter. And what it is, it's an instrument where you have some sort of reaction taking place, and it's sealed, and it's surrounded by water. And what we do is we measure the temperature change of the water, and from that we can measure the amount of heat that the reaction either gave off or absorbed from the water. So we use the temperature change of a certain mass of water to calculate the amount of energy associated with a particular chemical reaction. So it's called a calorimeter. We'll talk about this next week. Okay, let's define energy. Energy is the ability to do work. And by work, we mean force times distance. Anytime you apply a force to an object and have it move over a certain distance, you are doing work on that object. The unit for force is the Newton, and the unit for distance is the meter. And combined together, it has a unit that's called the Newton meter. If you've had physics or plan on taking physics, the Newton meter is a very useful unit in physics. However, the SI unit for energy is the joule, where 1 joule is equal to 1 Newton meter. So in other words, they mean the same thing. The Newton meter is handy in physics because you can see the unit Newton and you can see the unit meters, which sometimes you would cancel out. So they're kind of combined together in the joule. Now, SI, if you've forgotten, is the International System of Units. So every unit that we use in science is sanctioned by the International System of Units. So the joule is the unit of energy. Enthalpy, capital H for that. The internal energy stored in a substance. Also has the definition, the total heat content of a system. We cannot measure enthalpy directly. A chemical change must take place. So let me kind of summarize this. We have a substance, and in that substance is a certain amount of energy, like a cookie, say. We know that that cookie has a certain number of calories in it. Just sitting there on the table, we can't measure that. However, we can put it in a calorimeter, say, and measure the amount of energy that is contained within it. It has to undergo a change. Now, I'm about to show you a little video that might be disturbing to watch, so just brace yourself.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
Okay, that gummy bear had a certain amount of energy, and that energy, you can see, was released in this reaction. But just this gummy bear just sitting there on the table, we don't know how much energy it has. So the moral here is it has to undergo a change, and we'll be relating this to chemical reactions shortly. Every chemical reaction has an energy component. Either energy is lost or energy is absorbed. Like burning a piece of paper, energy is given off. Heat of reaction, delta H, is the change in enthalpy that takes place in a chemical reaction. So we go from reactants to products. So in like the gummy bear before, the gummy bear afterwards, you saw a lot of energy was given off. So delta H is going to be the enthalpy of the products minus the enthalpy of the reactants. The delta symbol, and this is capital delta, is used to mean change in. And you may have already seen this. Anytime you see delta anything, it's to be read as change in. So, and it's always final minus initial. So x could be anything that you want it to be. So if you have an initial amount, final amount, and subtract from that what you started with, that would be your delta x in this case. So products is what we end up with. The reactants is what we start with. So we take the enthalpy of the products and subtract that, the enthalpy of the reactants. This will make more sense in a few minutes. Now this is the definition of the change in enthalpy, the enthalpy associated with a chemical reaction. Now there's two possibilities. Either the reaction gives off heat or it absorbs it. So we'll look at these two examples, those two examples. Energy diagrams. First, we'll look at exothermic reaction. In exothermic reactions, energy is released. Just think of burning a piece of paper. That's a chemical reaction. It releases energy. You could think it more simply as just a ball rolling down the hill. Ball has a certain amount of energy at the top of the hill. As it rolls down, it loses that energy. Like the gummy bear lost energy as the reaction took place. Let me stop that. All right, so we're going to look at a diagram that we use to represent this. So this is the enthalpy of the reaction. Now, for all intents and purposes, and in every way conceivable for what we'll be doing, when I use the word enthalpy, simply think of it as heat. Remember, H represents enthalpy, and the H is directly related to the heat component. So when we say heat or enthalpy, just think of heat. And then this is time going by as the reactants are converted to products. So in an exothermic reaction, the reactants have more energy, more enthalpy than the products, just like the ball had more energy up here than it did down here. So if we measure the difference between the two, that's what we mean by delta H, a change of reaction, heat of reaction. And so remember, the definition of delta H is products minus reactants. And for an exothermic reaction, the products has less enthalpy than the reactants. So the products is a smaller number than the reactants because you have less enthalpy. So when you do that calculation, you're going to get a negative value. So, and you'll be able to, and you'll see it later in this unit, you'll be able to look up the enthalpy of a particular chemical reaction, and they're either going to be positive values or negative values. And negative simply means that energy is lost. It's not that it's negative energy, it's that energy is lost. It's like if I gave you $10, I am losing $10, you're gaining $10, but I'm not giving you a negative $10. The negative is just the direction of flow. So that's a very important component. Again, there's no such thing as negative energy. The negative just means that it's being lost. Okay, now another thing here, for an exothermic reaction, products are more stable because they have less energy content. So it's like the ball here is more stable below after it rolls down than it was above. When it was above, it had a certain amount of energy. And when you released it, it rolled down. But once it rolled down, it stabilized. Okay, and so that's the case for an exothermic reaction. The products are more stable. They have less energy content. All right, now the next is just going in the opposite direction, rolling a ball up a hill, and these are endothermic reactions. In an endothermic reaction, energy is absorbed or needed. Like rolling the ball up the hill, you have to put energy into it. Now for this reaction, let me stop the ball there, kind of drives me nuts. For this reaction, the products have more enthalpy than the reactants. Now, a good question would be, well, how does that reaction take place? How does a ball just spontaneously roll up the hill? Well, there's another component that we're not going to be getting to. If you take IB Chem 2, you'll address it. It's called entropy. Entropy is the measure of disorder. So there's another kind of behind the curtain component to this. We're not going to be addressing it, but just to kind of, when I first learned this, I was always baffled by, well, why would the ball roll up the hill? What's going on there? Well, there's another component. If you're interested in this, look up entropy. It's a measure of the natural tendency of things is to go from high energy to low energy, like the ball rolling down the hill. And then the entropy component is going from an ordered state to a disordered state. So in these reactions, the entropy overrules the energy component. I'm giving you far more information than you need, but just thought I'd throw that in there. Anyways, the ball rolling up the hill here. So the reactants have less energy than the products. So when we do the same calculation that we did before, the difference between the two, remember that delta H is still the enthalpy of the products minus the enthalpy of the reactants. But in this case, the reactants have less energy than the products. So when we subtract the enthalpy of the reactants from the products, that's going to give us a positive number. So when you have delta H negative, that means energy is given off, like burning a piece of paper, that's going to have a negative value. If it's positive, that means energy is absorbed or required. And like we talked about before, whichever has a lower energy is going to be more stable. So in the case of an endothermic reaction, the reactants are more stable. They have less energy content. Thermochemical equations, and this is what your homework will be dealing with and where the stoichiometry practice will come in handy. Chemical equations that include the enthalpy change that took place. So let's look at a couple of examples. Okay, in this reaction, nitrogen reacting with oxygen to form nitrogen monoxide, this is an endothermic reaction. It's a positive value. So this is called a thermochemical equation. Now, every chemical equation that you've seen in chemistry always had energy associated with it, always had an enthalpy value that you could look up for that particular chemical reaction. We just never mentioned it before. So don't think there's something special about this reaction. Every chemical reaction has an energy component. Okay, now we also can rewrite this. Instead of an enthalpy value off to the side here, we can include the value in the chemical reaction itself. And you can see that it's here. Now notice that it is a reactant, and that's because the enthalpy is a positive value. And remember, what does positive mean? It means it's required. So for this reaction to take place, we needed the nitrogen, we needed the oxygen, and we needed 100 kilojoules of energy. So positive, and you need, the main point here is you need to understand that both of these reactions give you exactly the same information, just in different ways. The delta H value here off to the side means that 180 kilojoules of energy is required, which means exactly the same thing here. It's included as a reactant. Okay, this is an exothermic reaction, nitrogen monoxide and oxygen giving us nitrogen dioxide. So it's exothermic. Now, exothermic means that it's given off. Remember, it doesn't mean that it's negative energy. It means that energy is lost. Okay, so when we write the chemical equation with the energy value included within it, it's going to be a product. So the negative value here means it's a product. Now, again, it's not, and I know I'm saying this over and over again, but it's because students are constantly trying to write it as a negative number down here. It's not a negative number. The negative means it's a product. Up here, the positive means it's a reactant. But in both instances, it's a positive value. It's, again, like if I gave you $10, I'm losing $10, you're gaining $10, but it's $10. At no point in time is it a negative $10. Okay, let's do a couple of practice problems, and this will be similar to the homework that you're asked to do. We're just going to do 2 problems, and that's it. How much heat will be released or absorbed when 5 grams of nitrogen reacts with excess oxygen according to the following chemical equation? So we have this is our chemical equation. Now, the energy associated here is for the 1 mole of nitrogen to react with 1 mole of oxygen to give us 2 moles of nitrogen monoxide. So that's the energy component for the moles in this chemical reaction. What we now need to do is convert grams to moles and then to energy. Okay, so always in any kind of reaction like this, or calculation like this, always start with the value that you're given. You're given 5 grams of nitrogen. So that's going to be your starting point. Now, anytime you go into a chemical reaction with a mass, the very first thing you need to do is convert that to moles, because the chemical balanced reaction is not grams, it's moles. 1 mole of nitrogen, 1 mole of oxygen, 2 moles of nitrogen monoxide. So the very first thing I need to do is convert that to moles. So 1 mole of nitrogen, you need to look it up on the periodic table. Remember that it's diatomic, so it's 2 nitrogens is 28.02. 1 nitrogen is 14.01. Okay, so now we can cancel out the grams, and that now would give us moles of nitrogen. But we want to go from the nitrogen to energy. So now I'm going to look at my balanced chemical equation, which tells me for every 1 mole of nitrogen, 1 mole of nitrogen that reacts, I will require 180 kilojoules of energy. Require or absorbed. So 32.1 kilojoules of energy is absorbed. And again, the homework is going to ask you to put in the correct word next to your answer. And so it's either going to be released or absorbed. And all you need to do is to look at the sign on the enthalpy value. Positive means absorbed or required. Negative would mean released. So since it's positive, it means it's endothermic and heat will be released. Okay, now when you do this calculation, I'm just a little fearful that some of you are having a little bit of problems with the calculations. Remember to always multiply the numerators, divide by all the denominators. So when you plug this into your calculator, it would be 5 times 180 divided by 28.02 equals. Or you could go 5 divided by 28.02 times 180 equals. Doesn't matter the order that you do it in, you just need to multiply numerators and divide by denominators. Also, do not multiply the numerators all together, write down an answer, multiply all the denominators together, write down an answer, and then do another separate calculation. I do not want to see that. You can do that on a separate piece of paper, but you're making your life much more difficult. Students will often say, well, I'm doing that because I want to be extra careful. Well, I would argue that you're setting yourself up for making a mistake more than if you were to do it the way I just asked. So the way that I'm asking you to do it is just in one step. 5 divided by 28.02 times 180 equals. The way that I described a minute ago, you would be doing 1 calculation, 2 calculations, 3 calculations before you get your final answer. And I would argue the chances of you making a mistake would be a lot more doing it that way. Okay, and one other thing, sometimes to double check your work, what you could do is instead of just doing it again, you could go backwards. So I could go to make sure that I got this answer's right. I could go 38.1, which is the answer on your calculator. So when you get your answer, just go backwards. I would divide by 180, multiply by 28.02, and hit equals, and I should get 5. Of course, I rounded the answer here a little bit, so it'd be slightly off. Kind of breaks the monotony when you check it that way, I think. All right, let's do one more practice. How much heat will be released or absorbed when 25 grams of nitrogen dioxide are produced according to the following equation? And so for this reaction, this is the amount of energy that is released. It's negative, so this is exothermic. Okay, so again, always start with the mass that you're given, include the substance. So I have 25 grams of nitrogen dioxide. So again, the first thing I need to do before I can use my chemical equation is to convert that to moles. So 1 mole of nitrogen dioxide is 46.01 grams, adding together 1 nitrogen and 2 oxygens. Grams of nitrogen dioxide cancel. And so now I want to go into the chemical reaction that tells me for every 2 moles of nitrogen dioxide, I will produce 112 kilojoules of energy. So that's my mole energy ratio. 112 kilojoules per 2 moles of nitrogen dioxide. And this is probably the biggest mistake that students make here, is to forget to use the coefficient from the balanced chemical equation when you do your energy to mole ratio. Okay, to type this into your calculator, it would be 25 divided by 46.01 times 112 divided by 2 equals 30.4 kilojoules. Because this is a negative value, it's exothermic, which means that energy is released. All right, so your homework is asking you to do a series of calculations like this, and these are the two examples you'd want to refer to. Each of the reactions you'll be asked to do, and there's 8 of them, will be either an endothermic reaction that we did before or an exothermic reaction. So refer to these two examples that we just did to do your homework, and you should be in pretty good shape. But for now, that is the end of notes.